morning. Thank you so much for the nice presentation, Asad. Today I'm going to present my PhD thesis titled as on automating performance problems detection in software systems through empirical analysis. My name is Muhammad Imran, and the thesis is supervised by Professor Vittorio Cortellessa, Professor Davide Ruscio, and Dr. Luca Traini. We will start with the motivation. Then we will talk about the challenges that are addressed by this thesis, and then we'll also look at the contributions which we did to address those challenges. I will look at them one by one, and finally we look at the conclusions followed by the future work. So first of all, we need to understand why software performance is important and why does it matter. So we know that it's a very critical non-functional aspect of software systems. In contrast to the functional correctness, we also need this non-functional aspect to be there. We also need to look for it and check for it. One of the reasons is that even though the software might be functionally working fine, there would be reasons or there would be times when your systems start to get slowed down. It starts eating more resources. But this happens with the passage of time, and it will not be very obvious just like the functional bugs. And this makes performance bugs different in their nature as well, because not only they're widespread, but they're also very subtle in nature. It's not easy just to look at them and say that this type of code or this type of pattern is a performance bug. One example here is the example of a snippet for a memory leak bug, which basically is happening because this function is opening an input stream and then closing it without doing any type of safety checking and making sure that let's say if some crash or some error occurs here, we close the stream before returning the method. Another important aspect of software performance is energy consumption, which has recently emerged as as an important dimension. And just to look at them, to deal with this type of aspects and to make sure that our systems are working correct non-functionally, we do the process which is called performance testing. And so performance testing is dealing with detecting of performance issues. And for doing that, we sometimes need detailed profiling, repeated executions of the tests, and then we are able to catch some of the bugs. So as I already said, this discipline is dealing with catching this type of bugs. It comes with its own challenges. Those challenges lie in the phases like development phase, maintenance phases, and execution phases. So for developing these type of tests, we really need experts. We really need different type of expertise, which are different than that traditional functional testing. And then for maintaining them, of course, it's expensive. We need to spend resources for doing that. And executing them is time consuming. So it's not like we just run and see if it's functioning correctly. We need to run it multiple number of times to get accurate measurements. And if we talk about the developers, they also need to know, what to prioritize, what should be tested first, or if we have limited resources, what should be tested and what can be left. They need precision. They need to know what should be tested. I mean, which part of the code is probably having bugs. And then the bugs itself are complex. They are not easy to, there are different type of patterns that they might need to understand. And so they might need assistance with that as well. And lastly, the energy efficiency. So they need to know the code that they're writing is how much energy efficient, or let's say the code structures that they're using, how they can affect the energy consumption in the later stages of the development or of the execution of the software. So the question comes that, is it possible to help these people? Is it possible to automate the detection of the performance problems? And to do that, we come up with a mapping of 4 different challenges on software performance engineering pipeline, and then we try to address those challenges with the help of contributions, which we saw in the outline of this presentation. I'll talk about them one by one. So the first challenge is related to the understanding of code coverage and its associated I can say another associated or tightly coupled aspect, which is the execution time. So we not only need to know how much code is covered by the performance test, but we also need to understand the associated execution time. And this is because it can help the developers to prioritize what to test. And to understand, of course, the coverage and the time cost. And then we also need to, the second challenge deals with the static source code features and the possibility of being able to predict or to characterize the code that should be tested for performance. The third challenge is related to the performance bug complexity itself, and we just test and we see that how the large language models more specifically can help us understand this complex thing, which is performance bugs. And the last challenge is related to the energy efficiency, and we really need to understand at the method level early in the early in the development cycle, that how small changes or how the selection of different type of code structures can impact on the larger scale overall the energy consumption of your software. So I'll start with the first challenge, and it is addressed by the first contribution, which also has resulted in a publication at EASE in 2024. So as I said, it is related to understanding the coverage and execution time, and we know that coverage generally for functional testing is used to assess the quality of your performance test suite. So we just need to evaluate the state of coverage for performance test suites. And as I said, that it is also associated with another characteristic, which is the execution time. So we really need to understand the relationship between these two. And generally they are very tightly coupled, but we really have to find the trade-off between, if we increase the coverage, we also increase the execution time, and vice versa. So we know that code coverage actually impacts the performance bug detection capability. So the more the coverage you have, that means you have better performance testing suite. But again, there is limited knowledge about what is the state of performance test coverage generally in the software system. So we try to address this with this study, and we try to design it in 4 different research questions. So the first 2 are grouped and related to the coverage itself. So we compare the performance test coverage with the functional test coverage, and then the second group is related to the execution time, where we compare the execution time of performance test with the execution time of the functional test. So just before I continue, as I said, coverage, in this study we deal with coverage in 3 different, I would say in 3 different meanings. So if we consider the scenario, we see that, let's say this is a performance test which is testing method 1, and in turn it calls method 3, 2 and 4. So we say that performance test A covers method 1, 3, 2 and 4. Whereas method 1 is directly covered by the performance test. So we differentiate between coverage and direct coverage. And let's say if there is another test doing the same thing, testing directly method 5, but also in general testing method 6 and 7 because of the indirect calls, and there is another aspect which is called related to method 2. We say that method 2 is covered by benchmark A and B both, so we say that this is the overlap. So we deal with these 3 different, metrics which we use in the study. So as I have already explained this. So for this study, what we do is we collect 28 different open source Java systems. We make sure that all of them have the benchmarks and the JUnit tests, and we extract different. You can say the coverage labels for almost 187,000 methods. We define the features where we try to see the coverage, the overlap ratio, just to see how much overlap is there in the testing suite. The scope tells the size of each test on average, and then we also see the execution time, total and average execution time. So to do that, we executed this process, which is in 3 phases. We start with preliminary selection. We do some filtering, making sure every suite has performance and functional tests. Then we do two type of analysis, which is the static and dynamic one. With the help of static analysis, we get what is the state of the methods, what are the methods in that project. And with the help of dynamic analysis, we see, with the help of profiling, we see which methods were actually called when these tests were executed. So the functional and the non-functional tests. Well, with the help of this, we get some data which we process later on, and then we build some reports which basically tells us the methods covered by performance tests, methods covered by functional tests, and their execution times. So at this stage, we know which methods are covered by which performance tests and what is the state of the coverage. So we are able to answer the first two research questions, and we see that the benchmark coverage, if we compare it to the J-unit test coverage, performance and functional testing, the benchmark coverage, the performance test coverage, is 4 times less than the functional coverage. Similarly, the direct coverage has the same trends where the J-unit tests are covering more methods directly as compared to the benchmarks. And if we try to compare the overlap ratio, it is in contrast to what we see in the first two scenarios, and we see that the benchmarks, the performance tests, have higher overlap ratio as compared to the J-unit tests. Well, this might be due to the fact that we might need to test, some multiple tests are targeting more important parts of the source code, and they are tested by multiple performance tests. And if we look at the execution time comparison, we see that although the coverage of performance tests is very low, but the execution time is very high. So that means that there is an inverse relationship. Even if there is low coverage, there is high execution time. So execution times are significantly varied from few minutes to almost over 100 hours. And they are very diverse across different projects. So we see the total and average execution times which confirm this aspect. And if you just look at the performance test, we see the slowest one is taking almost 90 seconds, in fact the fastest one, and the slowest one is 401 hours. Similarly, if we look at per single performance test level, we say one test executed in 30 seconds, and at maximum it took 7.2 hours. And now when we compare it with the functional testing, we see that the performance, the smallest test for J-unit test took almost 18 seconds to 821 seconds, whereas for JMS benchmarks it was from 37 seconds to almost 1600 seconds. So we see again more expensive in executing than the functional tests. Well, this leads us to think about that, okay, fine, if performance tests are taking really, much execution time and they are expensive as compared to the functional tests, that means we need to select, we need to be sure what we are testing more carefully, we need to prioritize what we should be testing. For this reason, we came up with a second challenge, and we try to understand if we can do this with the help of static analysis, which is faster, cheaper, less expensive. And this addresses, this contribution addresses this challenge, which is also resulted in one more publication in MC in this year. So we build again this study based on what I have shown earlier. So this is the addition that we are doing here, trying to understand what we already have. So at this point, we already have the coverage labels. We know which method is tested, which method is not tested. So we have the ground truth. What we need to do is we need to extract some more static features of all those methods and then feed them to the machine learning models and try to see if we can generalize few things. So we make 4 sub-research questions, again, which are related to the machine learning. So we start with the default settings, then we try to do some rebalancing and feature preprocessing, and then we do the hyperparameter tuning, and finally we even try transformer-based models to find out what's happening. Well, I'll just quickly show you here the features that we have collected. So in general, we have 45 static features. They are like, for example, number of for loops, number of if, number of switch and stuff. And they also have some other static features which are based on the usage of different libraries. So we make sure we see that, for example, in a particular method, if certain number of libraries are used or not. The table is not shown here, but of course those libraries are somehow associated, or they might, we think, might affect or you can say might be related to performance. We choose 11 machine learning models, which is listed here, and then we do again some some post-processing and try to see if we can improve the results in every sub-research question. We have already seen this process, and as I told you that we collected the ground truth here. So this part actually uses the machine learning, and of course we use the CodeBERT and graph CodeBERT, which are the transformer based models. So we start with the basic configuration, we try with class rebalancing, feature selection, and then we try with hyperparameter tuning, and finally we also try with the transformer based models. So the results again are not very good. I mean, by good I mean that but we thought with the help of those static features we are not very convincingly able to characterize what's happening. So we see the best performing models here are decision tree, KNN, and random forest with the default settings. And what we do is that we do the feature selection and class rebalancing, and we are able to again see that there is no huge difference, you know, in the performance of these models, and still random forest KNN keeps on performing better as with the default settings as well. And then for the third sub-research question, we compare with the default settings, and we do the hyperparameter tuning. So we see that with the default setting, in fact not with the default, with the feature preprocessing and with the class rebalancing, we see that the top 5 models which were performing include random forest. So we have different configurations where we have different sampling techniques, different feature selection techniques, and then we come up with the best F1 score, which is 0.46. Even after the hyperparameter tuning, this just improved to very little number, and you know, decision tree KNN actually kept on the lower levels. And then we tried to employ the transformer based models as well using the same data set. We trained the models, fine-tuned them with our data, and then we see that the best F1 score here is 0.34, which is even less than the best that we achieved with the traditional machine learning models. Well, this leads us to the third contribution, that okay, fine, if we are not able to, you know, characterize the code that is being tested, let's try to understand the performance bugs themselves. So we take help from the large language models, and this contribution resulted into, I mean, this is submitted to Saner. It's another publication. So to design this study, we try to employ and exploit the text processing capability of large language models and feed them with the source code and ask if they are able to tell us that this code particularly has a performance bug or not. We start with the default configuration of language models, that means the zero-shot settings, and then we try to give some examples to build the context and let's hope for the better results. And then finally, we also compare it to the machine learning results. So we start with the data preparation, we did some filtering, we came up with the training and testing sets, which basically allows us to feed the source code itself, the performance bugs, which are labeled already, which we know, to the language models. So we use zero-shot and few-shot prompts, and also we do the pre-processing. That means in one scenario we remove the source code comments, and in the second scenario we leave the source code comment to see if they also have some impact. They may be helping the models or they are the noise. And then finally we compare the results, do the prediction with the help of machine learning models, which are of course using the static features, and then we try to compare it with the results which we achieved with the language models. So for zero-shot and few-shot, we did not get very good results. The best one that we have, which performed with the inclusion of comments, is coencoder. The best F1 score is 0.024, whereas if we fine-tune that, this 0.024 improves to almost 46%, but in absolute terms it's not a very good number, although this just leads us to the conclusion that language models are not really understanding the characteristics of the performance bugs with the zero and few-shot settings. Of course, if you fine-tune them, the results can change. And even the inclusion and exclusion of comments was not having a huge difference. So we understand that LLMs actually fail to understand either with zero shot or with few shot. I mean, even if we give the examples and context, they are not able to produce results. And then we finally compare it to the machine learning models, and we see that out of all the machine learning models that we used, the language models are not able to perform better, except Quen and of course MLP and random forest were the models which were superseded by the language models. So we came with the conclusion that LLMs actually, although can process text, they can work with a lot of code scenarios, generate code, summarize code, but for performance bugs, we need to do something better. And finally, the last challenge related to the energy consumption is addressed with the other fourth contribution, which is resulted in another submission in ICPC, which is under review currently. So we all know, just to build the context, energy consumption is really important. It's, again, as I told, a key dimension of performance. But the main challenge with energy consumption is that if we need to measure it, like other performance testing practices, it needs repeated executions, it needs special environment, it needs hardware, it needs tools, and they are generally not really accessible. Sometimes the hardware is not available. So definitely we need some other way around to somehow estimate the energy consumption. For this reason, we again try to utilize what we have done before, the static features, less and cheap option, less expensive and easier option. So we extract the static features of the code and try to see if we can predict the energy consumption. And then we design the second research question where we try to improve with the help of feature selection and of course some post-processing. And finally, we try to improve the hyperparameters and see if the results are improving. So to design the study, we collected some study subjects. Of course, these are some written Java codes, which basically we can run, execute, and definitely we can measure their energy consumption. We collected some static metrics out of those Java codes. We did some energy profiling, because not only we did in the study, we used the static features, we also collected dynamic features, which is the energy consumption and the execution time. And we use this energy consumption as the ground truth, and we use this execution time as one of the dynamic feature, just thinking that it can support the models for predicting. We came up with a data set, we use some regression models this time, and then we do the estimation. So for the subjects, we have some Java files which we collected from computer language benchmarks game and Rosetta code. They are implemented Java programs, very self-contained, which we can run easily and measure their energy consumption, execution time, and also collect their static features. We use 11 regression models, and we use different types of feature preprocessing techniques, which gave us almost 77 different configurations. Okay, yeah, we use the same set of features. I think we excluded some of them, but yeah, the list is available. You can see that. Yeah, and for performance evaluation, we use basically we more relied on the R square and mean absolute percentage error. Okay, so to design this study, what we did is we did some subject selection after some filtering, making sure the code is executable, self-contained, do not need external libraries. We execute that code. Through the static analysis, we extract the static features, and then with the dynamic analysis, we collected the CPU utilization, which is the execution time, and we collect the energy consumption. And finally, we train with the help of machine regression models. For the collection of energy consumption and execution time, we use an isolated remote server where we are sending the commands from the client. These commands are executed on the remote server, and in an isolated environment, the energy and execution time are collected. So if we look at the results, random forest is the one which is again comparatively performing better. The results are really not promising, but relatively random forest works better in case of R square, mean squared error, and other metrics as well. And by looking at the feature pre-processing, we came up with the consistent results where random forest kept on performing better, except some of the models like decision tree really performed poorly even after the feature pre-processing. And we did some study trying to understand which features are contributing more to this energy consumption. So we came up with the results that the features like number of catch, number of do, switch, while, cyclomatic complexity and execution time are the ones which are selected by most number of feature selection techniques. And if we look at the SHAP values analysis, the log execution time has been contributing the most for the models, including the number of internal calls and the name length. So the name length appearing at the third number gives us an idea that sometimes it might also be possible that the names are the longer names, let's say, or the shorter names are somehow associated to energy. They show the intent of the developer that this particular method is more important than the other methods. So this naming selection is also sometimes important. And yes, the most contributing feature, which is the execution time, when it's excluded, the models really start to perform poor. Even although they are not performing better before, but yeah, they still drop their performance further. And the hyperparameter tuning did not bring much improvements. So we see that the top 5 performing models, which is random forest on the top, did not actually, I would say, improve much even after the hyperparameter tuning. This might be due to the reason that the data set is not very long, not very large, and adding the complexity of hyperparameters is still not helping the models. So related to code coverage, we conclude that we find that large non-performance tested regions are there in the performance in the Java systems, and the execution times are really higher. Also the overlap of the test, of the performance test, is really very high. The static source code features are really not helpful to understand the characteristics of the code that should be tested. Even the hyperparameter tuning and the fine-tuned transformer based models were not able to capture the complexity or the characteristics in that code. Taking the help for large language models, of course, we say that it's not a silver bullet. That means that for our scenario, it was not really helpful. We could not understand the characteristics of the performance specs. So they were not helping to understand the complexity, the complex nature of performance specs. And for energy consumption, of course, we were able to get some indicators with the help of static analysis, static features, and including one dynamic feature. But of course, these results or these indications cannot be considered as the final one. Rather, they can be used as a support or as guideline or as assistance. So finally, we say that we definitely need to make sure, by what we learned, is that we should follow the strategies where we try to balance the coverage and execution time. As I said, they are inversely proportional. So we really need to make sure we find a good trade-off. We explore some other representations as well, like some graphical representations. We see that the simple static features are not helping, so maybe we can try to explore some control flow, data flow graphs, or other program representations which are also static, but of course different. We need to link the method level predictions with workload profiles and the system level measurements. So we have the method level predictions, which are not really good, but we need to see them in a bigger picture, and maybe they are more helpful in that scenario. So we come up with the system level measurements, or we try to connect them with workload profiles, and they might be more meaningful. We need to extend tooling to support the developers, of course, for doing better performance testing. And finally, we need to reason about execution behavior by combining static code with domain specific information. So not only the static features or static aspects of the code is enough, not only other representations are enough, probably we might need to add some other domain specific data or information, feed that to the models and get better results. So as I have been telling you along the way, This thesis has resulted into 2 already published contributions, where the other 2 are already under submission, under review at SANER and ICPC. And finally, I would not be, missing this opportunity to thank this wonderful team. I really feel so emotional at this time. Well, I'm sorry. But yeah, this has been a wonderful journey. And I must thank Professor Vittorio Cortellessa, Professor Davide Ruscio, Luca Traini, Riccardo Rubi, who is remotely attending this, Professor Ivano Malavolta, and Vincenzo Stoico. So these 2 people are amazing. I have visited them for 3 months in Amsterdam, and the last contribution on energy consumption, this work was done here, and it was an amazing experience, I must say. Thank you so much. If you have any questions, you can ask.
Leonardo, you want to go first?
As you wish.
Yeah, let's do as you've done before.
Okay. So thanks for the interesting presentation. Congratulations for the work. I do have several questions. So maybe I more or less follow the order of your contributions.
Yeah.
So my first question is about the choice of computing coverage at the level of the methods. May you explain the rationale of collecting method level coverage in comparison, for instance, to more fine-grained coverage measure like statement or branch coverage that may give you a better view of the portion of the code that is exercised?
Yeah, we could do that, but one of the very important reason not to do that was we not only needed to get the coverage information, but we also needed to have the you can say we need to profile for doing that coverage, for collecting that coverage data. As you have seen that we use dynamic analysis. So the tools that we were using, for example, the profiler, the async profiler, is able to provide this, you can say, the profiling information at the method level instead of the statement or branch level, which is more micro.
Okay, so it is a tool reason, not a, let's say, scientific reason behind it.
Yeah.
Okay. Maybe a comment going a bit on the opposite direction. Collecting method. I wonder if collecting method level coverage really captures the performance problems that sometimes I think derive from a more like a global view of the system. So it is not only the case if a method has been executed or not, but maybe a performance issue may derive from a bad design of the system, and then you need a specific scenario and combination of methods to be executed in some order in order to really see the performance problem.
Yeah.
So I also wonder if it is, on the other hand, a bit too fine-grained compared to the kind of performance problem someone may want to detect. That is not just executing individual methods, but they respond to some more complicated patterns.
Mm-hmm. Mm-hmm. Yeah, of course, but just looking at the methods individually, as the results we see were not really good. For example, when we were trying to characterize the code that is tested for performance, this is probably due to one of the reasons that we might need bigger context. We might need not only to look only at the methods, but we also need to see them in a bigger context. Just instead of individual methods, we might need to look at the classes. So I think I would just agree with what you're saying.
Okay,
Yeah.
but have you tried to somehow derive such a bigger context in which the performance problems may arise?
But we try to collect the features at class level. So, for example, we try to see that the method which is in a class, that class contains how many other methods. Let's say, for example, the size of the class. Let's say. But yeah, again, connecting it to more bigger context, no, we did not explore that explicitly. But if you see, there are few features in our list of features which are at the class level.
Okay. And then may you explain the reason why you differentiated between direct coverage and coverage?
This was due to like when we were collecting the data provided by the profiler, we actually came up with this fact that we should not only focus on the methods which are directly there. In fact, this is one of the reasons we went for the dynamic analysis. We did the profiling because we could easily collect the methods that were there in the performance test statically, but it was more important also to see the methods which are called as a result of a method which is tested directly by the performance test.
Okay.
So yeah, I think it's important that it might provide you another aspect or intent of the developer that probably he might need to. For example, we just don't look at the bigger functionality. We also, with the help of this, we look at the functionalities associated to that one.
Okay, because I was thinking more to somehow distinguishing the purpose of the test that is maybe exercising a given functionality from the execution of some other utility methods that are necessary to bring the system into the right state before the actual operation is invoked. So I was thinking more to trying to make this distinction between, okay, I want to test this scenario, and this scenario consists of my test invoking a given method at the end of the test. But in order to exercise this scenario, first there are a number of preliminary operations that have to be completed, and then somehow I want to distinguish these two cases. But I see it is not exactly the case.
Yeah.
And so now I turn this into a comment in terms of the coverage. While you could collect data about the code that is executed, I still see this semantic difference between the target of the test, the purpose of the test that is exercising a given operation in a given state, from the rest of the code that is executed, that is just to reach the right state. And then this additional code that is executed is not really tested under that scenario. It just of course it is executed, but it's not
the intent was not to test that. The intent was not.
So in a sense, to me, it will be interesting to distinguish coverage in these terms. So what was really the intention of the developer, and what is just executed in the context of the test. This may give you a better perspective. Could be to me a more interesting distinction compared to direct and indirect. And I think in testing it is used this term for focal method to distinguish the method that is the purpose of the test from the rest of the methods.
Sure.
Okay. And in one of the experiments, you compute this gap between the coverage that can be achieved with the unit test and the coverage that can be achieved with the performance test. What can you really deduce from this gap? This is not entirely clear to me.
This is what we actually intended to understand. What's the state of performance test, and as a benchmark we use the functional testing. And we deduce with the help of that for example, for functionality we would want to test everything. We would want everything to function correctly. But for performance, probably number one, as it's expensive, and number two, we might not want every part of the system to be highly performing. So I think this is the reason why the coverage for performance tests is narrower as compared to the functional testing. This could be one of the deductions.
Okay, because but maybe it's my bias. It was also my initial guess. So somehow it's really what I expect. So you don't execute the whole code base for performance. You just execute the relevant scenario. So I expect to see the gap there, and then results are like confirming. Okay, people when considering the performance scenarios carefully select the scenarios. It's not an objective to execute the entire code base. When you write the unit test, you want to exercise. The whole code.
Yeah, exactly. So, for example, if you, of course, you won't remember it, but I just missed that there was one of the system which was we inspected annually, and we saw that this is a graphics library. In that case, the coverage for performance test was higher than the functional test. So this was one of the outliers in the results as well.
Okay.
Yeah.
And in the second contribution, where you try to make the prediction, sorry, could you clarify if the goal of the prediction is to predict the methods that are covered or the ones that are direct covered by the performance test?
The methods that are actually covered or directly covered, both, because the methods which are directly covered, of course, they are subset of the ones which are covered. So yeah, the goal is to see which method is covered, not only directly covered.
Okay, because for the same discussion we were having, not sure the target of the prediction should be predicting all the methods that are exercised, but rather kind of direct cover. I mean, what is the purpose of the test? Because some other methods are just incidentally executed in the context of the performance test. So I expect the prediction to point at the relevant method that has to be exercised, and then of course you need to build a more complicated test to exercise that method. But pretending to predict any methods executed in the context of any performance test, not sure the prediction technique I expect. I would expect the prediction technique to work in that way, because it would suggest a number of accessory methods that they should not be really the target of the test. Just to make an example, if you invoke a number of setter and getter in your test, then with this empirical setup, you pretend the predictor to report the setter and getter as methods to be exercised. But this is not what you want. You want the relevant performance methods to be highlighted, not all those
the high level
accessory methods. Yeah. Okay. And I think the conclusion is that based on your experiment, the static features are not doing great with respect in this in this setting.
Yeah, exactly. I mean, this could be the static features, plus one important aspect was the highly imbalanced data set. You know, the performance test, you will see the coverage is very low, so the labels for the methods which are tested are of course less than the ones the other class is in majority. So there could be different reasons, but generally the results are that we cannot predict in this setting what we have now.
But have you expected the results to have any insight about what this prediction based on static feature is missing? What are the cases that are like wrongly classified, and maybe how could you improve the quality of the prediction?
No, we did not investigate in this direction, but by the other study, which is on energy consumption later, we just included one dynamic feature, and we saw that it is contributing much already. So I think again, what we learned from this is that only static features probably is one of the problem.
Okay.
Yeah.
Okay. And have you considered because I see you have a sort of set of static features that are, let's say, in a sense, the frequently used ones when you do some kind of static analysis. And I wonder if, since you have the data set with performance problems, you try to inspect the problems and the faults and the examples you have to see if there are any, shared characteristics that may influence your choice of the static feature. So just to make a selection that is more problem specific rather than trying with, let's say, the commonly used ones.
If you're talking about the second contribution, the second study on static features and prediction, the data set that we have in the projects that we have, like they're not selected because they already have the performance problems, but it's just that they have the performance tests. So it's not sure that they have the performance problems. So we don't know this at hand. What we know is that what is tested and what is not tested by the developers by default. So. So yeah.
Okay. Maybe related to this comment, I would say just a comment about what you are really predicting to me. That is not what should be tested for performance, but what developers will test for performance. Which is not,
exactly. Because we are capturing, we are capturing this behavior from the. It's already the bias or the intent of developers is already there in our data set. And secondly, to answer your question on static features, like we chose not every static feature, we made sure that they are somehow related to performance, and we took this from the literature and other works on software performance.
Okay.
So for example, the libraries that we selected are not all the libraries in Java. There were very few, for example, the ones on concurrency, the ones related to file handling and stuff. So where we think, for example, there could be scenarios where they can affect performance.
Okay.
Yeah.
And then in the use of the LLM, I see in the prompts you decided to not explain what a performance problem is. I would like you to elaborate on this choice.
Yeah, I think we already had this comment from one of the reviewers in the paper as well.
It was not me.
Yeah. I think defining performance bug in just a prompt is not really possible because it's really complex itself. I mean, there are different types of patterns, different types of scenarios, but of course I agree that we can give some basic definition in the prompt. Probably that can help. But yeah, I agree.
Okay. And I wonder if you have any guess about if and how the performance will change with using bigger models or using most recent models.
Definitely.
Because LLMs are changing continuously. Now we have big reasoning models, and we see results are changing in few months. So I wonder if you have any guess if
you are
will
right.
be more or less the same or not.
Exactly, I would agree because using larger models would definitely impact, will allow us larger context window. So let's say, for example, the examples that we're giving in few short prompts, we picked the smallest possible examples from the code, and then we were giving it to the model. So of course, if we have larger models with the larger context window, will allow us larger prompts, and will allow us to provide more context to the model. And I think it can definitely improve.
Okay. And then have you tried to ask for an explanation in addition to a response to the LLM, in addition to the yes, no, to explain the reason why the model is suggesting something?
No, we did not, but even without that model,
the model could be right and maybe your guess could be wrong. So if you have an explanation, you could check who is right, let's say. Otherwise, it might be a bit more difficult.
Yeah, I mean, I would say it was the other way around. We were asking the model not to provide the explanation, but it was providing it. So we were having difficulty in limiting it to yes or no responses, and then even we had to post-process a lot of responses, trying to see if the model is predicted with yes or no. So yeah, but I mean, generally, yes, we did not try to ask for the explanation why it's doing so. Yeah.
Because, if the model claims that there is a performance problem, then it might be a bit hard to double check. But if there is an explanation, you can decide if the explanation is simply stupid and so the model is wrong, or maybe the model has detected a very tricky case that you didn't notice and the model is right. The explanation may help to cross-validate
exactly.
the result.
Yeah.
Okay, I think I have done with my questions.
Thank you so much.
Again.
Okay.
Thank you.
Thanks, Leonardo. Davide?
Yeah. So thanks a lot for the presentation. Gave to me a lot of food for thought.
Thank you.
Yeah, the first question is about the analysis you conducted. So basically you show that the coverage for benchmarks is way less than the one that you have for functional test cases, which is expected. But then I wonder the opposite. So I wonder why some methods, some classes are actually benchmark. I mean, did you verify why some methods are tested and for which reasons?
No, I think no. I mean, you mean even if the coverage is less, you want to ask that even why these methods are covered?
So let's say that you have one method
which is tested,
fully covered.
Okay.
Why it's covered?
We build the data set, like we take it from the projects, from the open source projects, and the performance test is written there, and we just we accept it. We say that okay, fine, if it is labeled as in the benchmark, we consider it as a tested method, but we don't look at the qualitative aspect of that.
Okay.
For now.
Yeah, then so an aspect that for me is always hard to understand. I mean, in my opinion, it is way harder to say that something doesn't work than saying that something works. Because if it works, you see it works. And then if it doesn't work, then something tricky happened, but then you have to understand why. So in your case, so for example, given your experiment with the large language models, given also what we just said with Leonardo, so the different aspects that one can consider, for example, the number of parameters of the models. Which other further enhancements do you see in that aspect? I mean, what could you do better to leverage more these large language models?
Generally, I mean, across the thesis, I would say, if I would like to leverage, I would like to leverage it with more information somehow, probably be it more context in form of, like, for example, for performance bug, just giving a loop and asking if there is a bug or not. Probably we need more context, because we need to see where this loop is, okay, which method this loop, by which method this loop is executed, and what's the purpose of that method. So of course, adding more context would definitely help. So I think one of this thing. And if we talk about, for example, the code which is tested for performance, probably just not looking at, like, if it was labeled as 1 because it was there in a benchmark, might not be enough. Probably we might need to consider other factors, like, for example, workload profiles, and other features like this. So
because also I was wondering that in some cases people use micro benchmarks to test integration issues. And then if you have only metrics that are at the method level or at the class level, maybe you don't see the
exactly the bigger picture. Of course. So in conclusion, I would just say, if there is a way, or all the ways which allow us to include the bigger picture, would be much more helpful.
Yeah, and then also when I was reading the reviews that you received, so one comment was about the fact that when you tried to estimate the energy consumption, then there is of course a connection with the time that is needed to run the methods, to execute the methods. But then you show that that's not enough. So you show that even if you take, of course, if you take that feature,
it helps.
It helps. But then even in those cases,
it's not enough.
It's not enough. So, go in the same line. What do you think it's missing?
I think more. It gives the idea that it helped. That means we can add more similar type of indicators or signals. So I think, like, for example, adding the memory consumption, or other dynamic features, like, for example, the environment, the features related to the environment itself in which the system is running, probably can help more.
Although then if you start collecting much dynamic information, then at some point
we go to state 0. Exactly. Then why? why do we need to have the static analysis? Of course. So as I said, of course, then I think we can somehow use it as an indicator that, of course, like, you know, narrowing down a bigger area, and then we at least are not required to rerun the whole system. Instead, we are much more focused. So we get the pointers, and then we continue with the regular or traditional approach. Yeah. Thank you so much.
So thank you very much, sir. Congratulations for your work. I have a couple of very precise questions, mainly on the choice that you have done during the setting up of the research.
Okay.
So the first one is also mentioned to one of the review report regarding the energy profile that you have selected. So because you selected one specific energy profile, and I would like to know a little bit more on the motivation that are behind of this kind of selection.
We used JALR-JX for profiling the energy, and one of the main reasons was, you know, of course, the nature of our study. It was for Java systems, and we needed to collect data at method level. So JALR-JX is one of the tools which, of course, provides us this at the method level, and yeah, I think this was one of the reasons.
Is there any other?
There are, I mean, of course, there are other tools, but for example, they would need you to somehow instrument your code, or probably, you know, so for our environmental setup, I would say it was much straightforward with JALR-JX. We could attach it with the JVM, and it could collect the measurements at the method level without even disturbing the code. So one of the motivations for us was to, you know, without altering the code, for example, we wanted to just measure the energy consumption. Yeah.
And a similar question regarding the 28 open source Java systems that you have selected.
Yeah.
Is there any reasoning behind?
Yeah.
What was the
the main thing was, like, we started with one of the existing studies from our research group, and we started with 40 Java systems, and even then we had to, you know, drop a lot of them, just because in some of them we were not able to execute the functional tests. The JUnit tests were not executing. For some of them, they were missing some versions of the JUnit. So the main idea and criteria was that they should have the performance test, they should be in Java, and they must also have the functional test. And of course they must be open source. One important thing, if you have seen in the list of systems that I showed, that they are from different domains as well. So we also made sure that they are from, like, for example, from games, from information systems, and from various domains. Yeah, but the initial collection of these 40 systems were from one of the previous studies, yeah, which also was based on these same motivations.
And the very last question regarding the future work.
You
have a long list of future work.
Yeah.
So is there anyone that you would select as a priority?
I would need resources first.
Yes.
And then I would definitely like to continue with the work on language models and the energy consumption. So as we already discussed, you know, adding more context, trying larger models, I think that can really help. And even with the previous work, which is on prediction of the performance risk coverage, I would really want to take help from, of course, as they are, you know, progressing every month, the language model. So I would definitely want to utilize them for where we did not succeed. I mean, by succeeding, I mean we did not get the positive results. So yeah.
Thank you very much.
Thank you so much.
Okay, thank you very much. Okay, thank you.
Thank you.
So now we move to my office, and I mean, I think that 10 minutes maybe, 5 minutes, 10 minutes, we'll be back. So I'm closing this call, and Leonardo, I mean, I will instrument, you know, the rest of the committee, and then you interact directly on several.
Well, I want personally, I am the supervisor of Muhammad Imran, to thank the committee members, okay, for their participation and the work done. Thank you so much. Unfortunately, today I could not be there in person because I have health issues, but thank you so much all the same.
Thank you very
Thank you.
much.
Thank you.
Okay, so we'll be back in a few minutes, okay?
Okay. सही थी. Thank you for coming, Sam. बहुत शुक्रिया. It was good. Thank you so much.
You did. You changed the introduction.
And it was really helpful. Thank you. Hello everyone. Assalamu alaikum. Thank you so much. Thank you Sam bhai. Thank you so much.
एक मिनट.
Everyone सिर्फ 4 लोग देख रहे हैं.
नहीं, ये 6 थे. अब आप इनसे बात कर लें.
मेरे ख्याल में कॉल कर लेता हूँ, इसके स्ट्रीम को बंद करते हैं. ओके एवरीवन, थैंक यू सो मच फॉर अटेंडिंग एंड आई थिंक आई विल जस्ट क्लोज. मुझे नहीं पता ये 4 लोग कौन है. आई थिंक यू गाइस कैन कमेंट मे बी, बट या थैंक यू सो मच वंस अगेन एंड से हेलो टू हसन, अब्दुल्ला, हुसैन से अस्सलाम वालेकुम. बहुत आपने तंग किया है. एंड मारिया कैसी हैं? ठीक ठाक हैं?